Hi everyone. Apparently we have no lights today. It's probably a sign I should have stayed in bed. I actually forgot to set my alarm this morning. And if it weren't for the fact that my bladder got completely full at 3 p.m. and forced me out of bed, I'd probably still be there. I mean, I'm sure you've all had this experience where you're in bed and you're dreaming about how nice it would be to pee. Then you wake up and you suddenly realize how nice it would be to pee. So you can all thank my urine for today's lecture. So today and Monday we're going to be talking about asymptotic analysis of algorithms, because I want you to have a good formal mathematical understanding of what it means when we say that an algorithm runs in big O of n squared time, or stuff like that. This is really important because the rest of the semester we're going to be studying algorithms and data structures, and we're going to be demanding that those algorithms and data structures be reasonably fast, and this is how we're going to measure one algorithm or data structure against another, is mainly asymptotically. So let's suppose that you write a program that manages the inventory for a nationwide chain of stores, and every night you have to process all of the changes that happened in the inventory in every store across the country that day. Now, maybe the amount of time it takes for your program to run is there's an initial startup cost of 10,000 milliseconds to read the inventory as it was at the start of the day in all the stores from the disk. And then once you've read in the inventory at the start of the day, you can start processing the day's transactions, and that might take 10 milliseconds to process each transaction. And in that case, if you want to process n transactions, where n is some large number usually, then that takes a total of 10,000 plus 10n milliseconds. Now, obviously the number 10,000 is a lot bigger than the number 10, but if your chain of stores does 1 million transactions a day, then you get the sense that this term is the one that's going to dominate in the long run. And so more generally, the study of asymptotic analysis is the study of how algorithms behave as the size of the data you're processing grows very large, or really as it goes to infinity. So we sense that this term here, the smaller looking term, is probably more important if n is very large. But we'd like to have a formal way of validating that intuition. And that's what asymptotic analysis is about. And I'm sure you've all seen big O notation before. And some of you probably have more sense of what it means than others. Now, big O notation is used to represent upper bounds on a function. And it has a very firm, formal mathematical meaning. It's not just hand-waving about how fast an algorithm runs. First of all, you should think of big O notation as sort of an abstract relationship between two functions. So the function often is the worst-case running time of a program, but not always. That's the main thing we use it for. So we'll talk a lot about algorithms running in big O of x time, and that tells us usually how fast the algorithm runs, but you can use it for other things as well, and I'll talk about that shortly. Usually when we use big O notation on the running time or the memory use of a program, there's some variable n which describes the size of the program's input. What do I mean by the size of the program's input? Well, you could measure the size in bits. How many bits of information does your program have to read off disk before it can process the inventory? You could measure it in terms of the number of items. Often that's more convenient. How many items do you want to insert into your linked list? But those just differ from each other by a constant factor. So usually for asymptotic analysis, we don't need to specify exactly how n is measured. Next, we're going to have some function that is a real-world function that describes some actual process in the real world. For instance, it might be the actual maximum running time of your inventory program in microseconds on an input of n items. And so this is an example of something that might be a t of n. This is the kind of function I have in mind. It's a complicated looking function and might be a lot more complicated looking than that. And so we want to abstract away all of the details that don't matter and compress it down to something simple. So we select a second function that we want to use for an upper bound. So fn is another function, but it's not an exact measure of something in the real world. Instead, it's something that we want to choose to be as simple as possible, so that we can convey how fast an algorithm runs asymptotically to another person without letting details get in the way. Now, having said that, I want to give you an informal definition of big O, and then I'm going to give a mathematically formal definition later. So just to get an informal start, I say that the real-world function, t of n, is in big O of some nice simple function, f of n, if and only if t of n is less than or equal to c of f times f of n. So c is some constant, and you get to pick the constant to make this work out. So this has to be true whenever n is big enough, and it has to be true for some large constant c. And you get to decide how big is and how large is. Your goal is to try to find a c big enough to make this fit underneath this. So, how big is big? Well, you need to choose n big enough to make the first function fit under the second one. I don't have enough room here. There. And how large does C have to be? And the answer is the same. So to really understand this, I'm going to draw a graph, and then you'll see what I mean. So let's start with our inventory function. So again, remember, the function we're looking at is t of n equals 10,000 plus 10n milliseconds. And we want to show that that's bounded in big O notation by a simple function. So we try one out. Let's try f of n equals n, because that's nice and simple, and we want the simplest one we can make work. So here's what the graph actually looks like. First of all, my function starts at 10,000 and then grows linearly. Like this. So this is t of n. Now I want to try out a function fn equals n. And if I just draw f of n equals n, then it looks something like this. Well, okay, that's not convincing. Definitely this function is never less than this function for any positive number. But I get to pick this constant c, and I get to make it really big. So let's forget about fn equals n. Let's just try a big value of c, like pick c equals 20. So what happens if c equals 20? Well, our function c times f of n starts out slow, because it starts at 0, but it picks up speed fast, and before you know it, it's bigger than t of n. So this is c times f of n, which is equal to 20 times n. And so at 20,000, or when the number of inventory items is 1,000, then it catches up to the true running time. And then everywhere to the right, it's bigger. C of f of n is bigger than t of n everywhere to the right of this line. Now, the main point that I want to get across is that what we care about is how these functions behave as n goes to infinity. So the fact that this line is below this line for a little while at the beginning is irrelevant. I can pick an arbitrary vertical line and ignore everything to the left of that vertical line. I only care about what happens to the right of my vertical line. And I get to pick the vertical line as far to the right as I want. And by picking the vertical line here, or here, or here, I can see that t of n is everywhere less than c times f of n. And that's what I'm asking for. So effectively, this proves that this complicated function is in big O of n. For any n greater than or equal than 1,000, t of n is less than or equal to c times f of n, as I promised. And therefore, t of n is in big O of f of n. Any questions about that? If you want to prove that this is true, then yes, you have to specify where that vertical line goes. If you aren't actually proving this, if you're just stating it, then you don't have to say where the vertical line is. When you just state this, when I just say t of n is in big O of f of n, I'm saying that that vertical line exists. Somewhere there's a vertical line, and to the right of that vertical line, this is always true. Other questions? All right, so I've tried to say this somewhat intuitively. Let me give you the formal version now. And this is the most important fact from this lecture. So what is big O of f of n? Well, actually, it's a set. It's a set containing a bunch of functions. It contains all of the functions t of n, no matter how complicated, that satisfy the following statement. There exist positive constants, C and capital N, such that for all little n greater than or equal to big N, T of little n is less than or equal to C times F of little n. That is the formal statement of what big O is. This is the key of today's lecture, the thing you need to really learn how to understand. And however abstruse this might seem at the moment, it will bear on every iota of your future career as a computer scientist. So it's worth, really getting a good intuitive feeling for what big O is. Now, formally, as I said, big O is a set. It's a set of functions. How many functions are there that satisfy this? Well, in general, there's an infinite number of such functions. So this is an infinite set. It's, those of you who know what this means, it's an uncountably infinite set, like the set of real numbers. So this is a really big set of functions. And that's the correct way to think of big O, although it's misused a lot in the literature. In the case over here, big N is referring to this number here. Big N is 1,000 for this example. Or in other words, big N is the place where I draw the vertical line to do my proof. So let me give you some sort of examples and important corollaries about how big O works based on this definition. First of all, a million N is in big O of N. How do I prove that? Well, it's really easy. I set C to 1,000,000. And now I'm saying that 1,000,000 N is less than or equal to 1,000,000 N, which is always true. So it doesn't even matter where I set my vertical line. Let's just choose any big N and this will work. So what the sort of moral lesson here is that big O notation does not care about constant factors in front of your running time. So when you write something in big O notation, you generally leave the constant factors out. You don't write big O of 2n squared. You write big O of n squared. You can write big O of 2n squared. That's a perfectly correct thing to write. But the whole purpose of big O notation is we want to express running times in the simplest form possible. And constant factors don't matter. Now, there's a reason for that. You may know that computers have been getting exponentially faster over the last 50 years. And so something that runs in 100 seconds today might run in half a second tomorrow. The constant factors vary based on how good a programmer you are, how good your compiler is, how fast your operating system is, how fast your computer is, all kinds of things. And the purpose of big O notation is to abstract out the parts that are independent of the architecture and depend only on the algorithm itself. So we want to evaluate an algorithm's speed independently of what physical medium it's realized in. So it's just unnecessary ever to write something like big O of 2n. It's not incorrect. I mean, mathematically, that's a perfectly good function. But it sort of defeats the purpose of big O notation, which is to simplify an algorithm's running time so that the person you're explaining to understands it. Any questions on that stuff, by the way? Yeah. Big O. I think it stands for order. So it was used by mathematicians, I think, even before computer scientists got a hold of it. And so they talk about terms being order n squared, order k squared. It actually probably started with very small terms rather than the very big terms that we're using. So you can talk about big O notation not only as n goes to infinity, but also as n goes to infinitesimal. And that was used a lot in the early days of, say, numerical analysis or even the study of converging series to see, how fast does a series converge to the exact answer. Yes?
So by this definition, can you say big O of n is a subset of big O of n squared?
Actually, you can say yes, exactly. Big O of n is a subset of big O of n squared. That's exactly correct. And I'm going to put up a whole table of these later in the lecture. Other questions? So here's a second example. One thing I want to point out is, and this is directly related to what that gentleman just said, is that n, the function n, is in big O of n cubed, or in big O of n squared, for instance. And proving that's pretty easy. Let's set c equal to 1. And capital N equal to 1. And I will draw this one. So again, our horizontal axis is n. Our vertical axis is the functions that we're looking at. And if you look at the linear function, it looks like this. And if you look at n cubed, well, the thing about n cubed is it always gets off to a really slow start. Its derivative is 0 at the origin. But once it gets going really fast. And so this is an example of where you have to move your vertical bar to the right in order to get the right answer, because n will always get off to a better start than n cubed, regardless of what constant you use. But eventually, n cubed will always catch up, no matter what constants are in front of those two functions. So somewhere there's going to be a crossover point where n cubed finally beats n. And for this particular choice, where my functions are just Tn equals n, and c times f of n is equal to n cubed, just the simplest versions of these functions, the crossover point happens at 1, at which point the functions are 1. And so that's where I'm going to sit my vertical bar and say big N equals 1. And everywhere to the right of that vertical bar, T of n is less than or equal to c times f of n, as promised. Now, there's a moral lesson, as usual, here as well. The fact that n is in big O of n cubed implies that if I say that an algorithm runs in big O of n cubed time, I'm not necessarily saying that's a slow algorithm, because it might run in big O of n time as well. So you need to know about that subtlety of what big O notation means. If you want to say that an algorithm always runs slow, there's another notation called big theta notation that we'll learn on Monday for that. But big O is an upper bound only. It is not a lower bound. And therefore, it can say that something is fast, but it can't say that something is slow. Next one, suppose I have a more complicated expression with a bunch of terms like n cubed plus n squared plus n plus log n plus n squared log n, so forth, so on. That is all in big O of n cubed. And you can prove this particular example by setting c equal to 3 and capital N equal to 1. I'm not going to draw this example, but what I want to point out here is that if you've got a bunch of different functions added together, and one of them grows a lot faster than the others, the one that grows fastest is going to dominate as you go further and further to the right. As n gets really big, n cubed is going to get really, really big, and n squared and n are going to follow behind so far behind that they're not even going to make a difference as n goes to infinity. And so big O notation is generally used to pick out the dominating term. And dominating means whichever one grows the largest, or the fastest growing. So big O picks out the dominating term in the function, and that's the one that we care about. So if an algorithm runs in this speed in milliseconds, we'll say it's in big O of n cubed time to keep things simple. Yeah? Well, so this is going to be another example where the crossover point is 1. So the question was, why do I choose c equal to 3? Basically, the n cubed function looks like this. The other function, well, let's make this the 3 times n cubed function. If this is 3 times n cubed, and that other function actually starts off linearly, then the crossover is going to happen here at 3, and this will happen at 1. And the reason why is that when n is equal to 1, what is n cubed plus n squared plus n? It's 1 plus 1 plus 1 is 3. So this wasn't the only option I could have chosen. I chose this just to keep it simple, because that way the crossover point is at 1. But if I had made this 2, there'd still be a crossover point. It would just happen later. Other questions? Yes? A lower bound is called big omega, and an upper and lower bound combined is called big theta. And we'll cover those on Monday. Omega, yeah, the Greek letter omega, last letter of the Greek alphabet. Other questions? Wow, you guys are really excited about omega. So there's a bunch of different big O phrases that come up over and over and over again in analyzing computer algorithms and data structures. And so I'm going to give you a long list of the common ones that come up again and again, and the names that you'll hear people use in casual conversation, or computer scientists in casual conversation, when they talk about them. So you can actually go smaller than big O of 1, but our table is going to start with big O of 1. And any function that's big O of 1 for some variable n is called constant. Means it doesn't get bigger when n gets bigger. That is a subset of big O of log n. And we already know an algorithm that runs in logarithmic time. It's called binary search. That is a subset of big O of log squared n. When you get into advanced algorithms, you'll find that these log terms can actually pile up surprisingly fast when you do really complicated things. So there are a lot of algorithms that have log squared terms in them. And that, any number of log squared terms multiplied together still grows more slowly in the limit than the square root of n. And square root of n grows more slowly than big O of n, which is called linear time, or linear space, or linear whatever, which grows more slowly than n log n. And we're going to see a lot of n log n algorithms in this class. N log n is just called n log n. It doesn't really have a name. And n log n grows more slowly than n squared, which is quadratic growth, which grows more slowly than n cubed, which is cubic growth, which grows more slowly than n to the fourth, which is called quartic growth. There are more names for these n to the fifth, n to the sixth that aren't used very often, so I'll just skip on to the big bad ones, which are called exponential growth. There are functions that, for very hard problems, that actually run in exponentially slow time. So if you see big O of 2 to the n, that's pretty slow. But you can get slower still if you see big O of, I don't know, e to the n. E is bigger than 2. This is also called exponential. But when you're in the exponential realm, it's not just constant factors anymore, though it may look like it. E to the n grows asymptotically a lot faster than 2 to the n. So this is exponential, but way more so. Algorithms that run in big O n log n time or faster are usually considered to be efficient. And algorithms that run in, say, n to the seventh or slower time these are usually considered useless. Algorithms in between that range, whether or not they're considered efficient or okay or bad or useless, depends on a couple of things. One being how large a typical problem is. So if you have an n to the sixth algorithm for solving Rubik's Cube, which actually does exist, then n with Rubik's Cube isn't very big, fortunately, so you can solve Rubik's Cube with the algorithm, so it's okay. if you have an n to the sixth algorithm for processing database transactions and you're, I don't know, Google, you're processing millions of transactions a day or billions, then n to the sixth is not going to do. It's n squared is not going to do. You're going to have to do better than that. Quick word about logarithms. I've said it before, I'll say it again. You need to understand logarithms, like not just be able to write them down on paper and do manipulations on them, but you need to understand them. You need to know them in your bones. If you can't say that's true about you yet, then study. Again, Goodrich and Tomasia, they have sections 4.12 and 4.17 that cover this material. You should know that stuff cold. You should know how to do manipulations with logarithms. If you don't know, say that log base a of b is equal to log some other base of b over log some other base of a, then you don't know enough about logarithms. Next, I want to give you some warnings about ways that you can go wrong with big O notation if you are not careful enough or don't understand exactly what it means. So, first of all, let's get started with a fallacious proof. So what I'm about to tell you is wrong. Please don't memorize this and tell me this is true on the exam. N squared is in big O of n. How do I know that? Well, it's simple. Just choose c equal to n. Then it becomes a simple matter of whether or not n squared is less than or equal to n squared. Because, remember, big O means that t of n is less than or equal to c times f of n. So that's the equation n squared is less than or equal to n squared. Obviously, n squared is less than or equal to n squared. So n squared is in big O of n. Somebody please tell me what I did wrong in this proof. Red shirt. C has to be a constant. Thank you. So you can pick C to be any constant you want as long as it doesn't involve n. Here's one that certain students always get stuck on. This is not a fallacious statement. This is the fact. Big O notation does nothing more than express a relationship between two functions. It does not say what those functions are. You have to specify what those functions are. So, for instance, the number of emails that you send to your mother as a function of time might be big O of t squared. In which case, not only are you a very good child, but you're an increasingly good child. Let's look at some examples of things that we could stick into big O notation, and only some of them are running time, okay? So in binary search on an array, the following facts are all true. First of all, the worst case running time is in big O of log n. This is what big O notation is used for more than anything else, but unfortunately some people sometimes fall into the illusion that that's all it's used for. No, I can use it for all kinds of other things. I can talk about the best case running time of binary search. And that's different because in binary search, sometimes you get lucky and you find what you're looking for on the very first probe. So the best case running time is, well, it would be correct to say it's in big O of log n, but it's also correct to say that it's in big O of 1. It's that fast. If you're lucky, then you're lucky. The memory use of binary search is in big O of n. We can also often talk about how much memory an algorithm takes. Binary search takes a linear amount of memory. You have to store all of the values that you're searching on. And finally, 47 plus 18 log of n minus 3 over n is in big O of the worst case running time. See, it's just two functions. It's a relationship between two functions. And I get to decide which function I put on the left side and which function I put on the right side. And those can be any functions I want. And every year it seems like there's a few students whose brains fuse when I use big O notation on an exam in any other way other than this one. And so when something like this appears, they just short out, you know. So please try to remember this and don't be that student. So are there any questions on that? White shirt, please.
Your table on the right,
Uh-huh.
where would n factorial go?
N factorial is as an exponent. It grows bigger than any fixed e to the n. I think it grows, I can't remember whether it grows the same as n to the n or it's a little slower than n to the n. Does anyone know? Slower. Okay. All right, good. So there we go. Any exponential is going to be a little bit slower than n factorial, but n factorial grows more slowly than n to the n. Yeah, that sounds right. I'm not going to ask you to prove that on the exam. Other questions? Other questions? Okay, next warning then. So I told you before that big O does not care about constant factors. But actually that depends on where the constant is. So if you just put a constant in front of a term and multiply it by 2, big O notation doesn't care about that. But it does care about exponents and things that are exponented. So for instance, here's more fallacious statements. Suppose I say that e to the 3n is in big O of e to the n because constant factors don't matter. Okay, this is where I want you to know that I lied when I said constant factors don't matter. Or to give you a similar example, is 10 to the n in big O of 2 to the n for the same reason, because constant factors don't matter? These are both wrong. Wrong, 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 wrong. And the way to figure out that they're wrong is just to divide. What happens when you take e to the 3n and divide it by e to the n to find out what this constant factor really is? Well, e to the 3n is bigger than e to the n by a factor of e to the 2n. And not only is e to the 2n not a constant, it grows damn fast. Likewise, 10 to the n is bigger than 2 to the n by a factor of 5 to the n. And that's definitely not a constant. So this is fallacious reasoning. And the final warning. Now this last one, please don't say this back to me on the exam, but this is a philosophical warning. It's not a mathematically correct statement, but it's something that you should know as a computer programmer, which is that big O notation doesn't always tell the whole story. Now, on exams, we're going to pretend it does tell the whole story. But as a working programmer, what you should know is, suppose we have, say, two different algorithms. Algorithm 1 runs in exactly this many microseconds, n log base 2 of n microseconds. And you have a second algorithm, u of n, which runs in 100 n microseconds. Now, big O notation suggests that you should always choose algorithm u over algorithm t, because obviously t of n dominates u of n asymptotically, meaning it's slower. Unfortunately, u of n is only faster than t of n in practice if n exceeds the number of what current estimates of the number of subatomic particles in the known universe. You see, this is a log 2 of n term, and log 2 of n is only bigger than 100 if n is bigger than 2 to the 100th power. And you're not going to be able to fit that many items into any modern computer, or even close, or any computer probably that will ever be built. So really, you can say that log 2 of n is less than or equal to 50 in practice. And that's something that you should think of when you're, in practice, choosing algorithms. Which algorithm you're going to implement for a particular implementation. If you know one of them has a really small or has a really big constant, maybe a log n factor is a better hit to take. And in fact, for most of you, you'll probably never have log 2 of n bigger than 30. Because even that fills up a 32-bit CPU. That much data. So any questions about any of this? All right, on Monday we will talk about lower bounds.